Hi there, we meet again. So, in the last class, we studied how lasing action takes place in a CO2 laser. The energy levels that participate in the lasing action, we saw that all the three ladders of vibrational modes, they participate in the lasing action in a CO2 laser. And we also saw what are the drawbacks when we make use of a pure CO2 laser gas mixture. We saw that the selective excitation may not be possible with a large efficiency when pure CO2 laser gas mixture is used. However, this can be overcome by adding nitrogen uh, to the lasing gas mixture. Nitrogen with its V equal to 1 being very close to the upper laser level of the CO2 molecule efficiently transfers its vibrational energy to CO2 molecule and therefore enables very selective excitation. And because nitrogen is a homonuclear diatomic molecule, it has only one ladder of vibrational energies, and therefore, this vibrational energy finally comes down to V equal to 1 and gets transferred to CO2. So the selective excitation is very well achieved by making use of nitrogen. And we have to understand that this energy difference is very small, much smaller than the kinetic energy, thermal energy of gas molecules, and therefore this is very efficient transfer of energy. Then the second drawback that we encountered when pure CO2 gas mixture is used is that the lower level depopulation. This depopulation is very difficult because it has to be done only through VT relaxation, that is, it has to be transferred into the kinetic energy of the molecules. And because the energy involved is very large, this is difficult. And therefore, by the addition of large amount of helium, this depopulation becomes very easy. Helium conducts away this extra heat through it as its own kinetic energy and delivers it to the discharge tube walls, from where it is conducted away by using a coolant, the water that flows there. And therefore, the efficiency of a CO2 laser is greatly increased by the addition of CO2 and nitrogen, helium and nitrogen. And the common gas mixture that normally one operates with for low pressure is 1:4, where 1 is CO2, this is nitrogen, and this is helium. Whereas for high pressure operation, helium can be as high as 10. And why helium has to be so high, we will see as the time comes. Now, here, as we are seeing this, we started with saying that CO2 in a CO2 laser, it is actually low vibrational transitions that are taking place. But here we have not really mentioned any rotational levels. What we have said are just the vibrational levels. So then what has happened to the rotational levels? Are they important? Of course. And why so? We will know. But before going to the rotational levels, we should know how population is distributed among various vibrational levels and various rotational levels. Now, vibrational levels, we know if we do not consider an harmonicity, they are equispaced, otherwise they get closer. So you have something like, so you have V equal to 0 to some V equal to N or even higher. So if the population here is N0, N1, N2, N3, and so on, then the population is distributed among these vibrational levels as per the Maxwell-Boltzmann distribution. And this is given by, if suppose we are talking about N2, that is the population here, in terms of N1, then N2 is N1 e raised to minus delta E by kT, where delta E is this, the difference between the two energy levels, delta E by kT. Right? So then how is the energy distribution? Population distribution. So this is the population and this is energy. So you know that the population in higher energy levels is much, much smaller, and the population increases as you come to the lower energy levels, right? Now, So it follows your that exponential decay. As we say, it is n is equal to n0 e raised to minus delta E by dt. So it is definitely dependent on temperature, and therefore, as temperature increases, the population in the higher energy levels also increases. As the temperature increases, population in lower energy levels reduces and population in the higher energy levels increases. So what would happen if temperature becomes infinite? What would happen when the temperature becomes infinite? So this is for T1, T0, T0 less than T1 less than T2. So as temperature is increased, the population in the higher energy levels increase. At when T is equal to infinity, you can see if you substitute infinity, you get n is equal to n0. So all the populations become equal, and so it will be something like this. So you probably must have read why by increasing the temperature of a gas medium, one cannot obtain population inversion. That is because the at most the population in the two levels, the upper energy level and the lower energy level, can become equal, but there can never be population inversion. Now, when we come to, so this is the case of vibrational levels. Now, when we come to rotational levels also, we know how rotational levels are placed. We know that they are closer and they slowly start becoming wider and wider separated. So these are, say, j equal to 0, j equal to 1, j equal to 2, and so on. So now, basically, it has to follow the Maxwell-Boltzmann distribution, and the population should be like this. However, in case of rotational levels, there is one more consideration that comes into picture, and that is that when a molecule is rotating, there are several planes of rotation which are possible, which are allowed. Okay. And for a particular J value, that is for a particular rotational energy, several planes are allowed, planes of rotation, right? That means different axes is allowed. So they all have equal energy, and therefore that particular J level is called degenerate. That means there is a multiplicity. Number of the molecule can have number of what would you call, the rotational axis is different and the plane of rotation is different. It can rotate in this direction, it can rotate in this direction, it can rotate in this direction. But are all the planes allowed? Because if that is so, then you will have infinite kind of multiplicity should become infinite for all J levels. It is not like that. The multiplicity G for a particular level J is 2J plus 1. So if J equal to 0, then the multiplicity is 0. That means there can be only one plane of allowed rotation. When J is equal to 1, it is 2J plus 1 is 3. So it can have 3 planes of rotation with equal energy, right? So as J increases, this multiplicity also increases. When the multiplicity increases, then the number of molecules which can go into those kind of rotations also increases, and therefore the population in that particular energy level also increases. So the population in any J level, for example, J plus 1, in terms of J, if we are trying to give, then there is this factor which is minus delta E by kT, which follows the Boltzmann distribution. And there is this additional factor which comes from the multiplicity or the degeneracy of rotational levels. So this factor increases with increasing J, and this reduces as the energy increases, and therefore there is a maximal effect. Initially, this factor is dominating, so you can see that the population is increasing, and as the energy increases, this factor, the exponential decay factor, dominates, and therefore the population reduces. So in the rotational levels, unlike the vibrational levels, the population is distributed. Population has a maximal distribution, and therefore this peaks at some particular value. Now, where it would peak, for example, I have just shown somewhere at around J equal to 11. So where it would peak will depend on the temperature. Depending on the temperature, there would be a kind of maximal effect which will be decided by these two factors, and the population would peak at that particular level. So while we have shown it to be like this for a particular temperature, T0. Now, as the temperature increases, once again, the population will increase on the higher levels and it will start reducing, and maybe it will peak at a, this is at a T1 less than T0. So for a lower temperature, the population will peak at a lower level, and for a higher temperature, population will peak at a higher as it goes to the higher J levels. I hope you have understood the temperature dependence. What I may just redraw it once again for your. So we have seen that there is a maximal behavior. It is somewhat like this, right? Let us say that it is for T0, and we consider a temperature T1 which is greater than T0. Then as the temperature becomes more, the population shifts to the higher level, and therefore you can have peaking at some other temperature T1, which is the J level is higher than what it is for T0. So the population starts shifting upwards with higher temperature. Now, so as we saw, the for distribution here is Maxwellian, and here you have a maximal behavior. So then now coming back to our CO2 laser, where we know that you have, these are the upper laser levels. This is the upper laser level, you have the lower laser level, and we have selective excitation with addition of nitrogen. And the molecules which are in various vibrational levels are distributed, as we said, in the various rotational levels of those particular vibrational levels as per the distribution that we just saw. So the distribution has a maximal behavior. It peaks at a certain J value. Here we have shown J is equal to 19, it peaks. So similarly, it has a distribution. Now, one important thing that you have to see here is that in the upper laser level, you find certain J levels missing. Can you see what are missing here? The even J levels are missing. Whereas in the lower laser levels, 020 and 100, the odd J levels are missing. Why this happens? This is certain symmetry consideration that comes into play, and therefore these even J levels are not allowed in the upper laser level 001, and odd J levels are not allowed in the lower laser levels, that is 100 and 020. Let us just remember it that these are because of certain symmetry considerations that these energy levels are absent in a CO2, right? So now, when population inversion is created between the upper level and the lower laser levels, so when a population inversion is created between the upper laser level and the lower laser levels, the transition, stimulated emission sets in, and therefore there is a transition of the excited species from the upper level to the lower level, giving rise to photons. As we said, when the stimulated emission is between 001 and 100, you have 10.6 micron, and when it is between 001 and 020, you have the 9 micron. So normally at the normal mode of operation, that is when the discharge temperature is about 400 Kelvin, it is generally 19 or 21 which has the highest gain, 19 or 17 which has the highest gain, sorry, it is not 21 but 17. And as we had already told, the 10 micron branch has much higher gain as compared to 9 micron branch. That is because we know that this 9 micron band is not actually optically allowed. However, there is a finite probability of these transitions, and therefore we have to make some special efforts for getting lasing here. But nevertheless, this is one of the lower laser level, this is the other laser level. So normally 10 micron transitions take place, and the transitions that take place are from G is equal to 19 to J is equal to 20. So as we have shown here, J is equal to 19 to J is equal to 20. This. So delta J is equal to plus 1, and this is a P branch. So since it is in the 10 micron band, so we write 10 first. Since this is a P branch transition, then it is P, and we write the terminating level, which is 20. So the nomenclature for this transition is 10P20. So this is the most normally encountered transition which happens in case of a CO2 laser. So you have 19 to 20, that is 10P20. The other one that could happen is 10P18. So this would go from 17 to 18. You understand, right? So when the transition is from 17 to 18, then, and still it is in the 10 micron band, so we write 10 P and 18 because delta J is plus 1. Now you may be getting a little confused because here when we earlier saw this, we said that delta J minus 1 is P branch, and now I'm saying delta J plus 1 is P branch. But then you see, if you just take two levels, J is equal to 0, J is equal to 1, and this is the upper vibrational level, J is equal to 0, J is equal to 1. Then this transition, okay, this is the absorption, that is delta J is equal to minus 1. And this is emission, right? The downward arrow shows emission. So here delta J is equal to 0 to 1, so that is plus 1. So this corresponds to the P branch, right? In case of absorption, it is minus 1, and in case of emission, it is plus 1. It corresponds to the same transition, same energy, and this is P branch, while the reverse. This is the R branch. This is the R branch, right? So you just have to say that this delta J for absorption and emission, the delta J is opposite. So in case of emission, delta J is plus 1. So this is your 10P branch. Similarly, if you want to think of 10R branch, so then it is delta J should be, for example, from 19 to 18, right? When it comes from 19 to 18, delta J is minus 1, okay, here. And we will say, and because it is still in the 10 micron band, that is 001 to 100, that is 10 micron band. So this is 10R18. We always use the terminal level for denoting this transition. So this is 10R18. Similarly, you can make nomenclature for 9P20, 9P18. I'm just saying 9P18 or 10P18 or 10P20, 10P18 because under the normal operating conditions, the kind of temperature you have in a discharge, these transitions are most common. Now, what actually happens when this lasing is taking place? You see, when we are saying that this, say this is 19 and it is coming to 20 and you have the transition, right? So, and we are having a continuous excitation. Now, when this transition is taking place, the population here is reducing, right? The population is reducing, population here is increasing. But you see, these rotational levels are very closely spaced. The separation between these rotational levels is few centimeter inverse, much less than kT. So, through collisions, there is a constant redistribution of population between these rotational levels so that this equilibrium is always tried to maintain. Otherwise, how do you have this population distribution, right? It is because that the population which comes to this vibrational level, there is a constant collisions between with other molecules, and eventually it assumes this distribution. So even during lasing, when we have lasing, the the population here reduces, this is called rotational hole burning. That means there is a hole which is burnt here. But when the collisions are rampant, in case of a CW system, there is a finally there is a balance. Initially, there will be some transients, but finally there will be a balance between the rate of excitation, the stimulated emission rate, and these rotational redistribution. That happens due to collisions. So that an inversion is maintained between these two levels, and a continuous lasing takes place, and we have a constant output. Yes, initially, when the lasing starts, then there are going to be transients where the population here reduces, the population here increases, the inversion changes. But in the meantime, there is also pumping, and therefore there is a lot of adjustment that keeps happening until an equilibrium position is reached. And once an equilibrium condition is reached, one has a continuous output from this laser on that particular transition. So normally, it so happens that the line that starts wherever the lasing has begun, generally that continues to laze because of this redistribution that is happening. Can you think of some time when such redistribution may not be effective? Well, there are such cases where your pumping is so very fast and for such a short duration that you don't allow this redistribution to happen. Then in that case, whichever transitions are above threshold, wherever gain reaches above loss, all of them can start losing. And therefore, of course, for the time you have excitation and you can have multi-line. But otherwise, in normal operation, what we see is that there is this rotational redistribution, and therefore this particular inversion curve is generally maintained. This particular population curve is generally maintained in the upper level as well as the lower levels, and you have transition on generally one line, which is normally what we say is 10p80 or 10p20. Okay, this kind of operation is called free running condition. That means we are not putting any effort to obtain lasing on any one particular line or some other. I'm not saying I want 9 micron, in which case I may have to do some additional work. Some I'll have to make changes in my laser cavity. But if I don't do anything, if I just have two mirrors and I have this lasing medium, then whatever output that is obtained, that is called free running output, and the lasing is generally on 10.6 is in the on the 10 micron branch on P20 or P8. Now, we have learned that our CO2 laser is highly versatile. It can operate in low pressure, it can operate in medium pressure, high pressure, multi-atmospheric pressure, and it can also work in longitudinal mode pumping, transverse mode pumping, CW operation, pulsed operation. Varieties of operating conditions are possible. So let us first look at low pressure CO2 lasers. So we already know how a low pressure CO2 laser operates. You have the CO2 laser gas mixture, CO2, helium, and nitrogen, which we know why we are taking now. And this is taken in a low pressure, maybe around 10 to 15 millibar, and is subjected to a electric field by means of a high voltage, by application of a high voltage, by application of a high voltage field between the two electrodes. Yeah. So if V is the voltage, V is the voltage that is applied, okay, and the separation between the electrodes is V. Okay? So the electric field is V by D. Now, any medium that we take, there are always some stray electrons. And these stray electrons, when they experience this electric field, then they get accelerated. And the acceleration is given by where E is the electric field, which is given by. So these accelerated electrons gain energy and they can cause further ionization of the species which are present in the gaseous medium. So when they cause ionization, there are more electrons created. These electrons will create further more electrons. They get accelerated, energized, create more electrons. So this kind of it creates an avalanche, and therefore a current starts flowing from the positive electrode to the negative electrode. And we say that the discharge is struck. Now, the electrons inside this, the electrons which are created, they need not be of the same energy. We know that they also follow this Maxwellian distribution. This is energy and this is the number. So there are electrons of various energies, and certain electrons of a particular energy are efficient in creating, in selectively exciting the CO2 molecules as well as nitrogen, as we saw earlier. So this will give rise to the population of the upper level of CO2 molecule, and also through collisions with nitrogen, the 001 level is selectively populated, and population inversion is created between the 001 level and the 100 that we have seen. So when a population inversion is created, then stimulated emission sets in from spontaneous noise, and the photons which are emitted through stimulated emission and that are along the axis of this resonator cavity, they undergo back and forth oscillation between the mirrors, oscillation, and a part of this intracavity flux is realized as the useful output. Now, as we saw just now, that this output normally would be on if nothing else is done. For example, we have just used two mirrors. One is 100% reflecting, one is partially reflecting. So this would normally be on 10p18 or 10p. So CO2 laser being very efficient, for 1 meter discharge, one can get as high as 50 watt under optimized conditions. Now, it is only, see, a lot of energy also goes as heat. We have seen that helium is required to depopulate the lower laser level, conduct away that energy as heat, and that is deposited on the walls of the discharge tube, which is conducted away by flowing water, which flows through the discharge tube and takes away that excess heat. So today we have studied about the lasing in a CO2 molecule, CO2 laser, the involvement of rotational energy levels, and low pressure operation of a CO2 laser.